Alright, so this video is going to be covering Chapter 12, Section 2, which deals with the solution process, namely how solutions form, the various parts of solutions, and how those parts interact. Now we're going to start off with just some common knowledge sort of things that you probably already know from experience, but for an example we're going to use, say, sugar dissolving into water. Now we're going to be discussing the factors that affect the rate of dissolution, and what that means is basically how fast the solute is able to dissolve. And the first factor we're going to be discussing is the surface area. So if you had, let's say, a cup of water and you were trying to make some sugar water, there's a few ways you could do it. First of all, you could take just a plain sugar cube and place it at the bottom. Or what you could do is take, a sugar cube, crush it up into a bunch of tiny little pieces of sugar, and sprinkle those into the water. And you probably know from experience that the little particles of sugar will dissolve much faster than the cube of sugar. However, you may not know because of a difference in surface area. Now, if you look at these two situations for dissolution, you'll notice that there's two very different surface areas. That is, for the sugar cube, there's only so many places where the molecules can come and pick up a piece of sugar to take and dissolve in the solution. The water molecules can only hit the outsides of this cube and take away sugar into the solution. However, because these pieces are much smaller per unit mass, they're all crushed up, water molecules can surround each individual piece as if it were a very small sugar cube. And because it can repeat this process many times for all the different very small pieces, it helps to increase the rate of dissolution. That is, it helps to dissolve the sugar much more quickly than if you just had a giant block where it would have to slowly chip away until you got smaller and smaller sugar cubes. Now, neither method will work very well if you just leave all the sugar sort of sitting there at the bottom. And this is because as the water molecules, chip away at the little crystals of sugar, what'll end up happening is that a bunch of sugar will build up around the area where it was taken from, and it won't really move. It has no reason to, go bouncing around. It will slowly diffuse through the solution, but it's not a gas, so the rate of diffusion is very long, or very slow rather. So it'll take a long time for this to completely dissolve just sitting here on the bottom. And one way to make this process go a lot faster is to take, a spoon or a stick or something and start stirring it around. And what this does, it'll take the sugar molecules and spread them out pretty evenly throughout the water, thus preventing a buildup of sugar where the water is completely full of sugar. That is, it's saturated, there's no more sugar that can be taken. And this evenly spread out sugar can then dissolve at a quicker rate because there's not a lot of sugar around it preventing it from being dissolved. Now, the final thing you can do to make solutes dissolve faster is to heat them up using, once again, some sort of poorly drawn flame. Now, once you heat it up, remember, temperature is just a measure of kinetic energy, that is, how fast things are happening. So these molecules of water, as they heat up, they're going to start vibrating faster and faster, and eventually some of them are going to start hitting this sugar pile. And because they have a higher kinetic energy, they're going to hit them with a lot more energy and force, thus taking them away from the pile a lot faster. And this also increases the rate of diffusion, meaning that the sugar will be able to spread out more evenly and thus lower, pockets of concentration throughout the solution. Now we're going to be moving on to a property known as solubility, and you may notice that as you add this sugar to your glass of water and keep adding it and adding it, eventually not all of the sugar will dissolve. You'll reach a point where you're just adding sugar and it's piling up at the bottom. And this is because as the sugar dissolves, the molecules leave this pile and they sort of, begin to float around among the water molecules, and eventually they reach a point where they're sort of evenly distributed. Now, simultaneously, some of these sugar molecules will, randomly find each other and hit each other and pile back together to form a crystal, like one of the little particles we have down here. So, at the same time that this stuff is dissolving, some of it, has a very low chance of hitting each other with a high enough energy to recrystallize. And eventually, as you keep adding more and more sugar, what happens is that these two processes of dissolution, which is again the particles leaving the pile and becoming part of the solution, and recrystallization, eventually these two processes will become equal as you have a higher and higher concentration of sugar particles within the solution. And at this point you reach something known as the solution equilibrium. And at the solution equilibrium, adding more sugar or whatever solute you're doing won't increase the concentration of sugar within the solution like we have over here, because the rate of crystallization is the same as the rate of dissolution. So just as fast as you're dissolving stuff in, it is recrystallizing to form that pile at the bottom. At this point, where adding more solute just results in a pile at the bottom, you've reached something that is known as a saturated solution. That is, it has the maximum amount of solute per unit volume that you're going to be able to reach at that temperature. And as you can see, if you were to add more water, the concentration of solution per unit volume would go down because there's more volume now. So you'd be able to dissolve away more of this pile, resulting in less sugar at the bottom. And if you were to add enough water to the point where this pile completely disappeared and all the stuff was dissolved and you could dissolve more still in it, you would have what is known as an unsaturated solution. Now, if you were to take this saturated solution where you have the maximum number of solute per unit volume and you were to lower the temperature to a point where it would normally be, able to have less concentration, you would have what is known as a supersaturated solution. And it's known as supersaturated because it has more solute than it would normally have at that temperature. Now, often these supersaturated solutions, if left undisturbed, can have these very high concentrations of solute. However, if you put something in the solution that begins to allow things to start to recrystallize, then what ends up happening is that this crystal will keep forming and forming until you reach a point where it's at the proper equilibrium for that temperature, where it is at its typical point of saturation for that temperature. And this is how things like rock candy are made, where you boil water and add a ton of sugar, and then you stick a stick or string or whatever in there, and as the water cools, the stick disturbs the solution and allows crystals to form on it, forming large crystals of sugar. And at the end, you're left with a regularly saturated solution like we have over here, and a large crystallized structure that took over the extra solute. Now, each individual solute is assigned a solubility value from some sort of experiment formed in the used in the past. For example, sugar and salt have different solubility values because they're different solutes. Sugar, for example, has a solubility value of 204 grams per 100 grams of water. And you have to specify a temperature because you'll remember solubility changes as the temperature goes up or down. So that's at 20 degrees Celsius. And for salt it would be different, and as well as other solutes. And for gases and their solubility, you also have to specify a pressure, because without the pressure the gases would be willing to just escape. And you can find these solubility values for whatever material you're using, usually in some sort of chemistry handbook. And most of the time they're given in 100 gram or 100 milliliters of whatever solvent you're going to be using.